Good afternoon, everyone. I am K. Siva, Laxmi, Assistant Professor of Physics, Dielectrics Engineering College. In the previous class, we have discussed about the dielectrics and polarization and different types of polarization. Now, in this class, we are going to discuss about the different types of dielectric materials, how the dielectric materials can be classified. So, depending upon the nature of dielectric materials, they can be classified into three categories. So number one is your piezoelectric materials, that is piezoelectrics. Second, ferroelectrics, and the third one is pyroelectrics. So piezoelectric materials, ferroelectric materials, and pyroelectric materials. So what is this piezoelectricity? So piezo means mechanical force. So the materials which are polarized when subjected to mechanical deformation is called piezoelectric materials. So mechanical deformation means we know that what is polarization? Polarization is nothing but the formation of dipoles. So in dielectrics, certain dielectrics, so they form the dipoles, that is dipole moment exists when we apply the mechanical force, that is called mechanical deformation. So the materials which are polarized when subjected to mechanical deformation is called piezoelectric materials, and the materials which exhibit this phenomena, those are called piezoelectric materials. Piezoelectric materials are very important since they permit the conversion of mechanical energy to electrical energy. So how we can justify this? Mechanical energy to electrical energy. That means we are providing the mechanical stress, mechanical force. So when we compress or elongate those materials, then what will happen? They forms the dipoles. The formation of dipoles, it produces the electrical energy. And this process is reversible. That means in piezoelectricity, what happens? So when we apply the mechanical force, electricity is produced. So conversely, it also true. That means when we supply the DC power, when we supply the DC current, then what will happen? Deformation will occur. That means the materials, they exhibit mechanical strain. Strain means the change in the length, the change in the dimension. So how we can define this inverse piezoelectricity? When a DC power supply is connected across an electrical axis of a quartz crystal. That means, so the quartz crystal, it exhibits your inverse piezoelectricity. Then the mechanical strain is formed. Mechanical strain. That means there is a elongation, there may be elongation, there may be contraction, there will be some change in the length, breadth, etc., the area, so whatever. So that phenomena is known as inverse piezoelectricity. Using this inverse piezoelectricity, we can produce the sound also. That means we can produce the ultrasonics also. That means when we apply the mechanical force, what will happen? The crystal is subjected to the mechanical state. So when the crystal or the material, when it is subjected to the mechanical state, a huge amount of vibration is produced. So using that vibration, we can produce the ultrasonic sounds. How we can, let us go to this definition. So when a DC power supply is connected across the electrical axis of the quartz crystal, then the mechanical strain in the form of either expansion or contraction. That means there may be increase in the length or there may be a decrease in the length will be produced. This phenomena is known as inverse piezoelectricity. So once again, so piezoelectricity and inverse piezoelectricity. In piezoelectricity, so when we apply the mechanical force, electricity is produced. That means electricity means the electrical dipoles are formed. In inverse piezoelectricity, so when we apply the DC power supply, then there may be expansion and contraction. When the crystal is subjected to expansion or contraction, then a large amount of vibration is produced. So using that vibration, we can produce the ultrasonics also. So first, next, ferroelectricity. So yes, we have discussed about the piezoelectricity and inverse piezoelectricity. So next is ferroelectricity. So ferroelectric crystals form an important group of dielectrics which exhibit a state of spontaneous polarization. This is very important point. Spontaneous polarization. Polarization is your formation of dipoles Spontaneous polarization means even in the absence of electric field. We know that the formation of dipoles occurs when we are supplying some amount of electrical energy. So in ferroelectric materials or in ferroelectricity, the certain materials they exhibit when there is the absence of electric field, they also exhibit some amount of polarization, which is known as spontaneous polarization. So this phenomena is known as ferroelectricity. Ferroelectric crystal form these are the very important group of dielectrics which exhibit a spontaneous polarization, and that's why they have a large applications in all the field. In ferroelectric state, centers of positive and negative charges do not coincide, and the materials have a net dipole moment even in the absence of electric field. That is, when there is absence of electric field, the materials they exhibit some amount of your dipole moment. So that is known as spontaneous polarization. Ferroelectric materials are called non-linear dielectrics. They are called as non-linear dielectrics because of the non-linear variation of polarization with the external electric field. So these non-linear variation leads to the closed loop called hysteresis. Here you can see the hysteresis loop. Okay, so they exhibit this hysteresis process. So that hysteresis process, or this is the graph between electric field and polarization. So how the ferroelectric materials they exhibit the polarization with the application of electric field. So when a ferroelectric material is subject to external electric field, how it changes, how the polarization changes. So this phenomena, this entire process is known as hysteresis loop. This hysteresis loop we can see in magnetism also. So in that case, the graph is between P and that is a magnetic field and your magnetization. But in this case, the graph is drawn between electric field and polarization. So that means a ferroelectric material, how it changes its polarization with the application of electric field, it shows. Okay, so initially, this is the first initial position. So when we increase the electric field, so what happened? Polarization also increases. When we increase the electric field, polarization increases. So with the increase in electric field, the polarization reaches a maximum point. Here I am keeping the cursor. So this is the maximum point. Okay, that means the substance is totally polarized. All the dipoles are polarized. So that means the material exhibits complete polarization. Okay, so that is your saturation polarization occurs at this position. So beyond this position, when we increase the electric field, there may be no change in the polarization. So after this point, when we increase the electric field, there will be no change in the polarization. So that means the substance acquires maximum polarization. Now, when we now beyond this position, this point, this peak, when we now let us decrease the electric field. When we decrease the electric field, the material it does not follow the same path. So initially it has followed this path. Now, when we decrease the electric field, it follows another path. This is the second path. Okay, so when we decrease the electric field, the polarization decreases. So when the electric field is zero, the substance inside the substance, the polarization is not equal to zero. So this position. Okay, so this position means it is called as your retentivity. That means retentivity means retaining the polarization. Even in the absence of electric field, the substance retains the polarization. So that is known as retentivity. So this phenomena, this is a very important point. This is retentivity, retaining the polarization. So that is that. Here we have written that in the absence of electric field, in the absence of electric field, the substance acquires the polarization. That is known as retentivity. Now, in order to, how we can reduce this polarization? In order to reduce to zero, we have to apply the electric field in negative direction. So when we increase the electric field in negative direction, that is when we increase the field in this direction, then what will happen? The retentivity, whatever the polarization is there, it will decrease to zero. It will to decrease to zero. So when we increase the negative electric field, the polarization becomes zero. And at this point, the polarization totally vanishes. So this is known as coercivity. So this position, this electric field is known as coercivity. Then how we can define the coercivity? So in order to reduce the polarization, the negative electric, we need negative electric field. So the negative electric field at which the polarization is zero is known as coercivity. So in this entire graph, you have to remember two positions. This x-axis, in y-axis, this is the position. This position is known as your retentivity, and in the x-axis, this position is known as coercivity. So retentivity means when the electric field is zero, the substance has some polarization. That means the substance retains some polarization, and that polarization is known as the retentivity. Now, in order to reduce the polarization, we need negative electric field. We have to change the direction of the electric field, which is known as coercivity. So how we can define the coercivity? So negative electric field at which the retentivity is zero is known as your coercivity. So the entire loop. So in this way, beyond this position, when we increase the electric field, the loop it comes toward this direction, and in negative direction it reaches the maximum point. And now when we reduce the field, it follows this path and reaches this point. This entire loop is known as your hysteresis loop. So, how we can define ferroelectricity? The materials which exhibit, the dielectric materials which exhibit your hysteresis loop or hysteresis process is known as ferroelectric materials, and the entire process is known as your ferroelectricity. So, how we can define in single line? So, ferroelectricity means the processing of polarization in the absence of electric field is known as ferroelectricity. So the example of dielectric materials which exhibit this ferroelectricity is your BaTiO3, barium titanate, lithium niobate, lithium tantalate. These are the good dielectric materials which exhibit your ferroelectric materials. And the ferroelectric materials are good dielectric materials because all here we have written this, all ferroelectric materials exhibit the property of piezoelectricity and pyroelectricity. Okay, so that means if you take the case of a barium titanate, it exhibits ferroelectricity and pyroelectricity. So all ferroelectric crystals are piezoelectric, but crystals may be piezoelectric without being ferroelectric. So quartz is piezoelectric but not ferroelectric. This is very important line. Quartz is piezoelectric but not ferroelectric, whereas barium titanate is both ferroelectric and piezoelectric. So that's why barium titanate is a good dielectric material because it exhibits because it's a ferroelectric material, and if it exhibits both piezoelectricity and pyroelectricity. Next we should know what is this pyroelectricity. Pyro means temperature. So certain materials generate electric charge when subjected to heat. Okay, pyro means heat. Certain materials generates electric charge when subjected to heat. This phenomena is known as pyroelectricity. So that means the temperature change in the material results in the change of position of the atoms, which in turn causes polarization. That means when we apply the heat, when we supply the heat energy, then what will happen? Inside the dielectric material, the dipoles will be formed. So when dipoles will be formed, there will be dipole moment also exhibits inside the material. So that process is known as pyroelectricity. So the change of polarization of the material causes the electric charge generation. Here, electric charge generation means before the application of electric field, that is heat energy, the positive and negative charges, they are at a particular point. They are concentrated. They are situated at a particular point. But when we apply the heat energy, that means pyro, so then what will happen? They will be separated from each other. So when they separate, when the positive and negative charge, they separate, they form the dielectric, or that means they form the dielectric moment. So this phenomena is known as pyroelectricity. So in brief, what is pyroelectricity? Formation of dipoles by the application of heat energy is known as pyroelectricity. So the example of pyroelectric effect, that means the materials which exhibit this pyroelectricity is your tourmaline crystal. So in brief, let us again go to the briefly the three different types of different types of electric material. So number one is your piezoelectricity. So what is piezoelectricity? Formation of dipoles by the application of mechanical force. And the second one, ferroelectricity. Ferroelectricity is formation of dipoles by the application of electric field, and the pyroelectricity is formation of dipoles by the application of heat energy. So these are the different types of materials, these different types of dielectric materials. So the example of the pyroelectric materials is tourmaline crystal. It is a single material which exhibit your pyroelectricity. Pyroelectric coefficient lambda, it is equal to dP by dt. P is the dP by dt. P is the pressure, T for temperature, rate of change of pressure. So every pyroelectric is a piezoelectric, but inverse is not true. So every pyroelectric materials, that means tourmaline crystal, is a piezoelectric, but every piezoelectric is not pyroelectric. So next, applications. So quartz crystal. Quartz crystal is very widely used for filter, resonators, and this crystal respond to pressure variation. So it is used as a pressure transducer. You know what is a transducer? Transducer, which converts one form of energy to another form of energy. So quartz crystal, it's a dielectric material. It is used for filters, resonators, okay, and for pressure variations, we can use this quartz crystal. Next, the Rochelle salt. It is used as a transducer in gramophone pickups, earphones, hearing aids, microphones, etc. For any sound instruments, we can use this Rochelle salt. It is in the form of a crystal. Piezoelectric semiconductors such as gallium sulfide, zinc oxide, cadmium sulfide they're finding application amplifiers and ultrasonic waves. These are the materials: gallium sulfide, zinc oxide, cadmium sulfide. They are used in amplifiers and for production of the ultrasonic waves. So the electro-optic devices are prepared using dielectric material. Electro-optical devices. That means or optoelectronic devices, or that means which converts electrical energy to optical light energy, vice versa. So for the preparing of this instrument, we can use this dielectric materials. Piezoelectric applications, production of ultrasonic waves, that is known as transducer. We know that what is a transducer, which converts one form of energy to another form. So production of ultrasonic waves, as earlier I told that is inverse piezoelectricity. So when we apply the ultrasonics, when we apply the mechanical force, when we apply the electrical DC voltage is applied across a dielectric material, then what will happen? There will be a strain inside the materials. Strain means there is a change in the length or a that is a contraction or elongation occurs. So during contraction and elongation, so sound is formed. That is that sound may be up to ultrasonics wave, in the range of ultrasonics. That's why we can produce the ultrasonic waves using piezoelectric materials. So this is a very important application for production of ultrasonic waves and transducers. Frequency stabilizers in crystal controlled oscillators, microphones, sonar devices used in delay lines and communication devices. These are the applications of piezoelectric materials. Next, ferroelectric application. So pressure transducers. That means what is a pressure transducer? So which converts variation of pressure into electrical signal. Okay, so pressure transducer, ultrasonic transducer. That means we can convert the sound energy into the transducer, which converts sound energy to electrical energy. So that is your ultrasonic transducer. So for the manufacturing, for the production of this, for the fabrication of this pressure transducer, ultrasonic transducers, and for the in computer device, RAMs, memory storage devices, ultrasonic waves generation, for the production of ultrasonic waves generation and using delay lines, communication devices to produce the ultrasonic waves, we can use ferroelectric application. So next, pyroelectric application. So pyro, we know that pyro means temperature. So temperature sensors, that means how the temperature is varying, how the temperature is changing. Infrared detectors and pyroelectric image tubes. In all these devices, we can use for the fabrication of these devices, we can use pyroelectric materials. So, using these are the applications, and they using using this concept, we can do some problems also. Thank you so much.